See what is modulation. BP. Suppose I have a data which say is 1, 0, 1. Okay. Now, generally what happens is in a communication channel, the probability of 1 becoming 0 and 0 becoming 1 is quite high. Okay. Why is because in semiconductor level only 0.3 volt difference is there. Okay, anything above 0.3 volt it will consider as 1. So it's very difficult to transmit 101 in a noisy channel. So what we do is we generally convert such data into polar data. Okay, 0 will be converted as -1. So see, if anything is 1, 0. Okay. If I write, okay, 1 into 2 will be 2, minus 1 will be 1. 0 into 2 will be 0, minus 1 will be minus 1. So this will convert, this formula is going to convert any normal data into polar data. Okay, so let us call P data is equal to data into 2 minus 1. Okay, so I need to transmit this polar data. Okay, for that, for BPSK modulation, I need to multiply the data with a sinusoidal carrier. Okay, if I draw a basic diagram of my strategy, suppose this is my data 1. So 1, minus 1 and 1. Okay, suppose this is my data 1, minus 1 and 1. So BPSK modulation is nothing but multiplying this signal with a high frequency sinusoidal wave. So sinusoidal wave should have more number of cycles per signal. Okay, so let us say that modulation index is 10. Okay, that means for each cycles I require 10 carrier signals. Okay, so define. So as usual, we should be able to define our sinusoidal signal first. Let us take frequency is equal to 1 kilohertz, sampling frequency is equal to f into say 100 times. Okay, Ts is equal to 1 divided by Fs. Okay, and any other thing, n is equal to, so I need to define the modulation index. Let n is equal to 10. Okay, so total number of cycle I will require is m into length of data, right? Now x, or let us say carrier, is equal to sine 2 into pi into f into t, where p is equal to 0 in the steps of Ts, n into t, where t is given by 1 divided by a. Okay, now if I execute this, you will see one interesting thing. What is it? I had 3 cycles of signal. For these 3 cycles, I have got totally 30 cycles of sinusoidal signal. This is okay, perfect. But the problem is I cannot multiply 3 with 30, and this is just an impulse. But if we look into our strategy data, I cannot modulate impulse signal. I have to convert that impulse into a pulse whose width is 10 times less than whose time period is 10 times less than the time period of the sinusoidal signal. Okay, so I need to first convert this signal into a pulse signal. How? Look, if we see clearly, this pulse width can be thought of as sample signal, where sample values are repeated. Over the time period, same sample values. Okay. Now, when we look at the sinusoidal period, each time period is known as TS. Okay. Each time period is known as TS. So, if I repeat the current signal after every TS time period up to into T period, then under that situation I will be getting same number of samples as the sinusoidal signal. Okay, so now convert impulse data to pulse, that is square pulse. So, T pulse is equal to 0 in the steps of TS up to T okay, this is the pulse width. Okay, so let us take one variable called extended data. For I is equal to 1 to length of data. Okay, and for j is equal to 1 to length of pp. Okay, ex data is equal to, I'll keep on repeating the data sequence, data of I. Okay, so figure 2, that is next figure, plot say ex data comma and I'll hold on such that in the same plot I can also plot the carrier signal, say with green colors. Why this is like this? The length, extended data length is 3003, carrier is 3001. Why it is, TP minus 1, because TP is starting from 0 here. So and this signal ex data zero, not data. In fact, I had converted the data into polar data. Okay, let me give read on. So such that this is in a much better fashion. Okay, so this is my message signal. Okay, this is my message signal, which should be multiplied with the carrier signal in order to give me the modulated signal. Okay, so the process of modulation should be modulated signal. Modulated signal is equal to extended data dot star carrier. Okay, let me also plot the modulated signal on the main signal itself. So plot modulated signal, that is M signal, say cyan color, for understanding, let us first make M is equal to 2. Let the message frequency and let it be only 10, so that we can clearly show the symbols. And let me put it with blue color, which should be, we should give a clear understanding of signal. Okay, this was my message signal. The green one, okay, they were the carriers. So the concept of BPSK signal is till the phase is same, the signal continues. Here you can see the signal has changed the phase, that is 1 becomes -1. So modulated result has also changed its phase. It continues with the same phase. Here again -1 becomes 1. Again the signal has changed its phase. Okay, so this is the modulated signal now. Okay, now this modulated signal will be going through the channel. Okay, okay, so channel signal is given by, say, receive signal is equal to AWGN. We need to define a signal to noise ratio. The higher signal to noise ratio is, the effect of the noise will be that much lower. So modulated signal will be passed through AWGN channel with the specific SNR. Okay, so plot M signal with plot receipt signal with green color, line width 1, let us display it in a new figure. Okay, so once we execute, see this is what is happening. This red color, this was the channel signal. Okay, that is, this is what I had actually transmitted, but because of the effect of the noise, the signal is getting changed. Okay, so let us say grid on, such that Now let me increase the SNR value to great deal. So signal power, we assume that it's 50 times the noise power. Okay. So you cannot actually distinguish between the signal and the noise. Okay, both will be almost similar. The variation will be very little. Now how do we demodulate? The demodulation is nothing but multiplying the signal, received signal, with the carrier again. Okay, so demodulation. What we are going to do is, my received signal is Rx. Okay, so demodulated signal is equal to Rx dot star the carrier signal. Okay, plot demodulated signal. Alright, from the demodulated signal I need to get back 1 and minus 1. Can you tell me how we can get back 1 and minus 1? I can add all the signal up to TP period. If it is greater than 1, then that should be 1. Again for next TP period. If it is greater than 1, then it is, greater than 0, that is 1, else it is minus 1. Okay. So you can clearly see, after multiplying with the carrier, positive cycle will come at the top and negative cycle will come at the bottom. No, after demodulation, the next part is decoding. Okay, so for decoding, this loop is going to come handy. How? Now, how we are going to decode? Okay, Sn equal to Sn plus let us take one variable k is equal to 1. Okay, so my received signal is nothing but, my demodulated signal is demodulated signal. K is equal to k plus 1. At the end of this loop, if, so let us say the received signal is null. Okay, at the end of the loop, if Sn is greater than 0, we'll say receive is equal to, okay, let us keep 0 itself. Okay, and at the end, let us print data and receive signal. Data was 101. We have also received 101. Okay. Now, what if I increase signal to noise ratio? I decrease signal to noise ratio. If I decrease signal to noise ratio to say minus 5 dB, that means I am inducing a lot of noise. Let me reduce it further. Okay. Okay, the bits gets changed. You can interestingly see, as you decrease SNR, okay, your noise power gets much more higher than your signal power. Okay, and one that should have been like this has got changed something like this. So if you consider this, here there is a phase change, here there is a phase change, it is not being able to maintain the phase. So because of that, it degrades. Okay. Now, there is an interesting thing that I want to do over here. Let me take SNR is equal to 15, a decent bit of noise. Okay, and it should be able to still detect. Now let us say this system has two users. One is transmitting at 1000 Hertz, another one is 2000. Okay. So if instead of 1000, if I take it say 1500, will the system still give me result? It should give me result, right? So changing the carrier frequency has got no bearing on the system.